to graph this function. That's what we're trying to do. Good. So we know this is a polynomial function. Degree.
3.
Very good. Max possible number of turns.
2.
2, indeed. The degree minus 1. Perfect. Domain, please. Like any polynomial function. All your numbers, indeed. Negative infinity to infinity. Let's get the table going. I put a domain. I make myself a mental note. It cannot have more than 2 turns. It doesn't have to turn at all, but it cannot have more than 2. So the maximum possible number of turns is always the degree minus 1.
Oh, the degree minus 1.
Yes, since the degree is 3, 3 minus 1 is 2. So it cannot turn more than twice. It doesn't have to turn twice, but it cannot turn more. Then we found the x-intercepts. How do I find the x-intercepts for any function? Very good, which is x cubed plus 2x squared minus x minus 2 equals 0. Perfect. Now what? How do I solve such a polynomial equation? Chapter 1. By grouping, very good. So let's group. From the first 2, you will factor out. Very good. What is left in parentheses? What do I have to have coming from the other 2? Otherwise, I won't be able to continue. X plus 2. And do not forget to write the equal symbol and 0. Only now let's discover. What is it? Negative 1. So from these 2, we can pull out a common factor, which is x plus 2, and then x squared minus 1. And then we know how to factor x squared minus 1. We did this on the first day of classes. Very good. X plus 1, x minus 1. It happens that I have to write exactly, so if you want to write it here, degree 3, 3x intercepts. Always. Even if they're all the same.
Wait, can you go back up to where you wrote the
Sure. So the same with 3x intercepts. Mandatory. Good. So we have 3 solutions, negative 2, negative 1, and 1. They all have multiplicity 1. So when I put them in the table as negative 2, this was negative, as negative 2, negative 1, 0, and 1, right on top of them, I'm going to say cross, which is a regular cross. Not flat, not slow, just a regular cross, because the multiplicity is 1 for all of them. Now we determine the y-intercept with 0, 0, 0, negative 2. So y-intercept, f of 0 equals negative 2. And now the end behavior. Let's talk about this one more time. For odd degree and for even degree.
So odd degree with n going down.
So it depends on the leading coefficient, correct. So odd degree has 2 options. Odd degree has 2 options. For a positive leading coefficient, it goes from negative infinity to infinity. This is the rule. For a negative leading coefficient, it goes from negative infinity to infinity. How will I remember this? Very easy. Just remember the linear function has degree 1. It's the simplest polynomial degree 1. And I know to graph a linear function, if it has a positive leading coefficient, that it's coming from negative infinity going to positive infinity. So this will be always the case for any odd degree. You will compare it to just a linear function, nothing else. Yes?
So the first one, it goes from positive infinity to negative infinity, and then the second one goes from negative infinity to positive.
If the leading coefficient is negative, it looks like this. Remember the linear function?
It looks like it's written the same right
she's
there.
asking if it's written. Where's the negative?
Right.
So one goes this way, the other one goes that way.
Exactly.
Can you draw that?
Yes.
Okay.
Yes, I'm going to write it one more time. Very good point. So first of all, if the leading coefficient is positive, it's going from negative infinity to positive infinity.
Okay. Oh, you're drawing it like those are the endpoints of a line. Like
Yes.
I drew it. Okay.
Okay.
There we go. We're good.
No, but I want to write it one more time. Let me write it one more time. It's a very good idea. So for odd degree, and the leading coefficient positive, it will look like this.
Oh, there we go. Thank you.
We read from left to right. So for negative leading coefficient, it will look like this. I don't know how many turns it has. I don't know what's happening in between. I don't care. As long as the degree is odd and the leading coefficient is positive, it will look like this. The degree is odd and the leading coefficient is negative, it will look like this. Like the linear function with a positive slope, like the linear function with a negative slope. Odd degree, compare it or compares to linear function. Same thing. It behaves identically. Now for the even degree, it will behave identically with what? Compares or behaves to the next in line after the linear. Of course, quadratic.
Oh.
Right? So any even degree will either come from positive infinity to positive infinity if the leading coefficient is exactly. We graphed it in 3.1. Or it comes from negative infinity going back to negative infinity if the leading coefficient is.
Oh, because the only time you have even is when you're gonna have it do the little max and mins where if it's an odd, it has a random. Okay.
Exactly.
Yep.
So the leading coefficient positive, it will do this. From positive infinity to positive infinity. And when the leading coefficient is negative, we'll do this. From negative infinity to negative infinity. So let's review this before we move on. Any odd degree with a positive leading coefficient will look like the linear function with positive leading coefficient. Any odd degree with a negative leading coefficient will look like the linear function with a negative leading coefficient. Any even degree with a positive leading coefficient, like x squared, coming from positive infinity going back to positive infinity. Any even degree with a negative leading coefficient, from negative infinity to negative infinity. And there is nothing else. Any function will fit either this category or this category. Polynomial, of course. That's what I meant. Good. So in our case, going back to our function, the leading coefficient is positive. The leading coefficient is positive, and it's odd. The degree is odd, and the leading coefficient is positive. So then I will say, and have to be negative infinity to infinity. I will have to say something about symmetry. And remember the symmetry, we talked about it in chapter 2. F of negative x will be negative x to the third plus 2 times negative x squared minus negative x and minus 2. You know what I'm doing. I'm replacing. That's what I have to do. I'm replacing x by negative x all the way. This is how we determine f of negative x. For symmetry, yes, for symmetry. So this will be negative x cubed. This will be positive 2x squared. This will be positive x and negative 2. Well, this will never equal negative f of x, and it will never equal f of x. How will I know that too? So I do know because a function that crosses at negative 2, negative 1, and 1 cannot be symmetric. It's not possible. So I will say not symmetric. It's not odd, not degree. We're not talking about degree. It's not symmetric, not odd, and not even. It's not symmetric with respect to the y-axis. It's not symmetric with respect to the origin. Now we're ready to graph this function. I'm not interested in looking at anything else but my table, because all the information is summarized in here. I don't care about anything else but this table. Here it is. So please watch for a moment, and then I'll let you, or if you want, up to you. So first I have to plot negative 2 comma 0. Then I plot negative 1 comma 0. Then I plot 0, negative 2. And then I plot 1 comma 0. And here's what the table is telling me. Come from negative infinity and have a regular cross at negative 2, 0. Something must happen here because it has to come back and cross at negative 1, 0. So it must have a maximum because it comes back and crosses here. Then it continues to 0, negative 2, but I don't know if it turns here. I don't know if it continues, and I don't know if it does this. So 1, 2, 3 possibilities. In college algebra, we cannot determine that. We have to look at the graphing calculator. But all I want to show my professor is that I know what I'm trying to do. I don't know how high this is. I will never know. I have to use calculus for that. So I will find that height because I have to add max min. But I don't know, and I'm going to just show 3 possibilities. And I'm not going to erase any. I'm just going to cross whatever and keep the correct one in a minute. So it comes back. So it either turns here, or here. I haven't looked at the function. You pick the function. But these functions are continuous smooth functions, meaning if I have to twist my wrist to graph, it's very unlikely that this is going to be. So I felt some pain doing this. I doubt that this is the case. So I just have to have something very smooth. But it may happen. That's why we're going to use the calculator in a minute. I think that this is a possibility, but I think that this is more probable. But I don't know. So it comes back, it crosses at 1, 0, and continues to infinity. And this is the graph of f of x, x cubed plus 2x squared minus x minus 2. Yes, we have to put it in the graphing calculator because we are asked to find the max min. I don't know what this is. It may be up here, or it may be down here. I don't know. I don't know where this turns. It may turn on the y-axis, and then the minimum is negative 2, but it may not. Okay, so let's put it in y equals. Here it is. In y equals. I have to execute. And then plus 2x squared minus x and minus 2. I graphed the function already. And coming back to what I already have, just for 1 second, I know that the entire action is here. Yes, it's true. I don't know how low this is. Maybe it's a negative 15. I don't know. Maybe this one is a positive 20. But for now, I'm just going to use the standard viewing window and see what happens. Negative 10, 10, negative 10, 10. So let's go to window. And what you can do is just pick zoom and 6. Zoom 6 is standard. And press 6 and enter. And here's the graph. And there are basically no secrets. It appears that it turns on the y-axis. I don't think so. Yes, Priscilla, go ahead. Any questions?
Where did you press up to?
6, standard. Zoom 6. So I see it's coming from negative infinity. I see it crosses at negative 2, 0. It has a maximum, a local maximum here. We'll determine it in a minute. Comes back, crosses at negative 1, 0. Crosses for sure at 0, negative 2. It continues to the right-hand side of the y-axis, where it's turning, crossing at 1, 0, going to infinity. So I do have two unknowns here. This is the unknown. It's the maximum between negative 2 and negative 1. So we go to second and calc. We want to determine a maximum. We're going to choose 4. And the calculator is asking us, okay, you want the maximum between what and what? Well, I want the maximum between negative 2 and negative 1. Oops. So as you see, the calculator shows us where we're looking for the maximum. And now it says a guess. I don't want to guess. Just press enter again. And it will give us the maximum. And the maximum is when x is negative 1.5 and the maximum is 0.6. I will put it in my table right here as negative 1.5 and 0.63. And I'm going to say that this is a local max. Then I have to go for the local min. So let's go for the local min now. I see the local minimum. Any questions? Go ahead. Any questions? Okay, so local minimum, I'm going to say this time, not to miss anything, I'm going to say it's between negative 1 and 1. So second and table. I'm sorry, second and calc. I want the minimum this time, which is 3. And I wanted to find it from negative 1 to 1. So the calculator is showing me where it's looking for the minimum. It's looking for the minimum where I gave it, or asked to look for the minimum between negative 1 and 1, and it will give us this. And obviously it's going to be to the right-hand side of the y-axis. I don't want to guess, just give me the minimum. So the minimum is at 0.2, and the minimum actually is negative 2.1. So I will put it in my table. So 0.2 and negative 2.1. And this is the local min. And now we know absolutely everything about this function. With the exception of one thing, but that is not a requirement in this class. But everything else we do know. One thing is missing, but it's not required. Yes. Yes, you can use mine. Any turn. Any turn. The turns have to be determined. They can be max or they can be min.
Or either or.
For the function, any turn has to be found. If there are 5 max and 2 min, you have to find all of them. It's not going to be the case. I'm just giving an example. All turns have to be determined. Some of them are max, some of them are min. I think we should continue with an even degree. And we had of the even degree, if you can remind me what it was, I forgot. There was the other function, f of x equals, I can look. Do we have it?
F of x equals negative 2
Yes?
x
Squared?
by 4.
Is x to the 4th?
Yes, ma'am. Plus 4x cubed.
Good. Perfect. Thank you. So what is the degree of this function? Very good. Max possible number of turns. Excellent. The first example took us a while. You'll see the second will be much faster once we understand what's happening here and what we have to do. All we have to do is fill out our table. Once we fill out the table, we have, except the symmetry, we have all the information we need. Okay, so let's start the table. Can anyone give us a domain of this function? Of course, it's a polynomial function. Very good. Excellent. Okay, degree 4, how many solutions or how many x-intercepts will you find? 4 x-intercepts. 4 x-intercepts. Good, let's find them. What do I have to write in order to find the x-intercept? Very good. Negative 2 x to the 4th plus 4x cubed equals 0. Yes, but since I can simplify both sides by negative 2, I will to make my life easier. So I have x to the 4th minus 2x cubed. Yes, the smaller the numbers, the easier to work with. Good. What will I factor out now?
X cubed.
Very good. What is left in parentheses?
X minus 1, 2.
Very good. And you said from the very beginning, because we established that, you said you're going to give 4 solutions. I'm waiting for you to give 4 solutions.
So 3 of them are going to be 0.
Excellent. Multiplicity.
3.
What does that mean exactly? Cross or turn?
Then it's
Even degree. Even multiplicity is turning.
it's gonna cross, but isn't it a wider cross?
Yes, cross flat. Excellent. And the last solution, you said x equals 2. What is the multiplicity?
1.
What will the function do there? Exactly. Just a simple straight cross. Excellent. So 0, 1. Make myself a note. Cross flat.
So why is it crossing flat again?
Because there are 3 solutions.
Okay, where are you getting the 3 zeros
From x cubed. X cubed is x times x times x.
Okay.
Very good. So then 0 and 0. There is no point in finding the y-intercept because I already found it. When x is 0, y is 0. It's this point, right? So the y-intercept, f of 0 is 0. We already have it. Okay, so it's in descending order. Careful. What is the leading coefficient?
Negative.
Good. So now, since it's degree 4, which function do we compare it to? So we don't have to memorize that. Are we compare it to
A quadratic.
quadratic? Either this or this. Which one? That's why we studied the quadratic
I'm
first.
sorry, it would be down.
Exactly, because the leading coefficient is negative, which means the end behavior is negative infinity to negative infinity. That's all it means. We're done. We just have to mention one word about symmetry.
Oh, whatever.
Yep, f of negative x. It's impossible for this to be symmetric. If it crosses at 0 and crosses at 1, it cannot be symmetric with respect to the y-axis or the origin. So f of negative x, negative 2, negative x to the 4th, plus 4 times negative x to the 3rd. And this will be negative 2x to the 4th and minus 4x cubed. This is not negative f of x, and it's not f of x. Not symmetric. This is it. That's all we need. So now we can graph.
It is not symmetrical because of what's the
Remember, in chapter 2, we said that f of negative x equals f of x. It means that the function is even, which means symmetric with respect to the y-axis. And if f of negative x equals the opposite of f of x, the function is odd, which means with respect to the origin, symmetric with respect to the origin. But this doesn't happen for this. This will not equal this, and this will not equal this. So therefore, the function is not symmetric. It's nice when the function is symmetric. It's easier to graph, but not all functions are symmetric. Ready? Let's see what we come up with. That's all I care about, my table. Yes, you can find as many points as you want. You can plug in any x value here, here, here. It's a waste of time. There is no need. But feel free to find any, plug in any x, find any y you want. So let's start. I see 0, 0, and I see 1, 0. That's all I have, basically. It's coming from negative infinity. It crosses at the origin in a flat mode. Okay, fine. See the difference between this and this? Perfect. Then it has to turn, because it comes back to cross normally at 1, 0. So it has to have a maximum. It crosses straight and go into negative infinity. I'm done. So this is f of x, negative 2x to the fourth plus x, 4x cubed. And you can say you're not done because you haven't determined this maximum. True, but I can't by hand. I have to put the function in the graphing calculator. So let's take a look. In y equals, clear the previous function, and let's put negative 2x to the fourth plus 4x squared. Right? Negative, yes, plus 4x cubed. Sorry, 4x cubed. Perfect. So now I know what to expect, more or less, right? I'm going to use the standard viewing window again. Zoom 6. And then I will adjust the viewing window if I want to see a better picture. Yes, I want to see a better picture. And I copied 1. I'm so sorry, forgive me. I copied 1 instead of 2. My apologies. So this is 2. Sorry about that. So it crosses here at 2. I don't know why I copied 1. I have to erase that. My apologies. It was 2. The other solution was not 1, but 2. Sorry. Good. So let's look at the graphing calculator. I would like to see this better. You can zoom in or go to the viewing window. And let's say negative 4 to 4 for x with a scale of 1. And let's say negative 2 to 8 or 6 with a scale of 1 for y. I want to just see a detailed, a better graph. So it's coming from negative infinity. See the difference? There are 3 solutions x equals 0. That's why the cross is so slow, flat. Here there is only 1 solution x equals 2. Straightforward. So now we can determine the maximum. It's definitely between 0 and 2. So second in calc, I'm asked to find, I need to find the maximum between 0, enter, 2, enter, and enter again. And it's giving us 1.5, 3.375. Can anyone give us the domain of this function? I'm going to have to put it in the graphing calculator. So it's at 1.5. The range, forgive me, sorry. 3.375.
So would it be
From,
negative infinity to 3.375
that's it.
with a bracket at the end of
Exactly.
3.75?
That's it. So we can write it down. So this is the range, negative infinity, and 3.375.
When you were finding the maximum
Yes,
and you adjusted the viewing window,
yes. Only because I wanted to show a better graph to see the difference between. You don't have to do that. But the reason I did it because I wanted to show and point out the difference between and how important the multiplicities are. Here the multiplicity is 3 and here the multiplicity is 1. So we can see the difference. That's why I wanted to zoom in. So here was the viewing window. One more time, negative 4, 4, 1 and negative 2, 6, 1. So I just wanted to show this difference. Huge difference. Why? 3 solutions, x equals 0. 1 solution, x equals 2. Very good. Let's look at the word problem now. Because we looked at these functions, and the question is, okay, nice, but what for? Let's take a look. Okay, see where we apply those. Ready? Okay, so here's an application. Here's a graph. During a diagnostic evaluation, a 33-year-old woman experienced a panic attack. A few minutes after she had been asked to relax her whole body. The graph shows the rapid increase in heart rate during the panic attack. Okay, part A. For which time periods during the diagnostic evaluation was the woman's heart rate increasing? Time in minutes. From 1 to 4. And then from?
8 to 10.
Excellent. We know this from chapter 1, right? Chapter 2, right? We know how to read the trend. We're not interested from what till what. We're interested when that happened. Between the first minute and the fourth, and between the 8th and the 10th. Excellent. Part B. For which time periods during the diagnostic evaluation was her heart rate decreasing?
4 to 8.
Yes, from between 4 and 8, indeed. And between 10 and 12. Awesome. Excellent. Part C. How many turning points occurred during the first 12 minutes? Remember, turning points from increasing, turning point to decreasing, turning point from decreasing to increasing, turning point from increasing to decreasing, turning point.
3.
I see 3 points. 1, 2, 3. Excellent. Here's the next question. Suppose that a polynomial function is used to model the data displayed. What degree? Use the number of turning points to determine the degree for the polynomial function of best fit. Right? Because a degree 4 will have 3 turns, maximum 3 turns. You can say, what if I choose a degree 15 and it has only 3 turns? It's possible.
Can you show again how you have the 3 turns?
Up, down, 1 turn, down, up, 2nd turn, up, down, 3rd turn. Better?
No, one more time. Just one more time. 'Cause you look
Up
at
and
the-
down, 1 turn, down and up, 1 turn, up and down, 1 turn.
I would say 4.
But this is not a turn from up and down, it goes up. That's why we were
Right,
asked.
okay.
That's why we were asked when it's increasing, when it's decreasing, when it's increasing, when it's decreasing, so we can identify the number of turns. Is that better?
Yeah.
Excellent. Good. So we will fit at least, it could be more, but at least a 4-degree polynomial that will have a maximum 3 turns. Is that okay? Yes? Perfect. Is there anything else? Should the leading coefficient, if we are fitting a 4th degree, should the leading coefficient be positive or negative? Right. Right. With maximum 3 turns. It has to be negative. Degree 4 has to have negative leading coefficient. Otherwise, it would be like this. Okay. Use the graph to estimate the woman's maximum heart rate during the first 12 minutes. Can we estimate the maximum heart rate during the first 12 minutes?
The maximum would be 115.
115. The next question, when, after how many minutes did that occur?
10.
After 10 minutes. Good. Use the graph to estimate a woman's minimum heart rate during the first 12 minutes.
63.
Okay. And when that occur? After 8 minutes. So now see how much insight we have about functions and about polynomials by simply looking at a chart of blood pressure, right? Heart rate every minute between 1 and 12. Any questions? Any questions? Okay, so let's take a look at